Good morning, students. That is, in the last session, we discussed about the order, molecularity, and how to find out the unit of rate constant of a reaction, as well as the pseudo first order reaction, and how to assign the order of reaction. That is, let us familiar with two questions which is already asked, or which is previous questions for your board exam. That is, calculate, question is calculate the overall order of a reaction. Calculate the overall order of a reaction which has the rate expression, that is, here there are two rate expressions. One is rate equal to K into molar concentration of A raised to half into B raised to 3/2, and for the second one, the rate equal to K into molar concentration of A raised to 3/2 and molar concentration of B raised to -1. There is already two rate equations, rate laws or rate expressions are given. And I think all of you know about the order. What is the definition for order of a reaction? Order of a reaction is the sum of the powers of reactant concentration expressed in the rate equation. Here, the power of A is half and that of B is 3/2. And how we assign the order? Order of first question equal to 1/2 plus 3/2. 1/2 plus 3/2 equal to 2, isn't it? 4/2, that is equal to 2. Order of this reaction is 2. And in the second question, again, sum of the power means 3/2 plus -1 or 3/2 minus 1. That is equal to 1/2. 3/2 minus 1. Isn't it? Thus, we can assign the order of reaction. Order is the sum of the powers of reactant concentration, and molecularity is the actual number of atoms or ions take parts in a chemical reaction. And also, by analyzing if the unit of rate constants are given, then you can predict the corresponding order of the reaction. The question, identify the order. Identify the order of a reaction. Identify the order of a reaction for each of the following. For each of the following rate constant. The rate constants are given along with their unit, and by looking through the rate constant or unit of rate constant, predict the corresponding order of the reaction. The first one is K equal to 2.3 into 10 raised to -5 liter mole inverse second inverse, and the second one K equal to 3 into 10 raised to -4 second inverse. Generally, the expression for unit of rate constant is mole raised to 1 minus and liter raised to n minus 1 second inverse. Or for a zero order reaction, the unit of rate and rate constant are same, that is moles per liter per second. Moles per liter per second. Liter, mole inverse, second inverse. What is the unit of, don't get confused, mole per liter per second is the unit of rate constant of a zero order reaction. Here it is for a second order reaction. Okay, order is 2, here it is first. For a first order reaction it is second inverse. Clear? And the next we have a derivation that is called integrated equation. Integrated equation for zero order reaction. Integrated equation for a zero order reaction. You know, zero order means those reactions whose rate constant does not depend upon the concentration. And let us consider a general example. Consider a reaction. Consider a reaction. A gives products which follows zero order kinetics. Consider a reaction. A gives product which follows zero order kinetics. Then the rate law minus dA by dt proportional to a raised to 0, because the rate of a reaction does not depend upon the concentration. A raised to 0 means any quantity raised to 0 is equal to 1. Or minus dA by dt equal to k, because k into a raised to 0 means k into 1. Or minus dA equal to k into dt. K into dt. Then the rate constant is found out, or the integrated equation for a zero order reaction is found out by integrating this expression. On integration, you know, dA combines to form A, that is integration, just like polymerization. Larger number of monomers combines to form bigger molecule. Here the differential combines to form integrals, that is dA combines to form A. And on integrating this above expression, on integrating the above equation or here equation what? Above equation, that is minus integral dA equal to k is the proportionality constant, k into integral dt. That is dA on integration gives A, that is minus A equal to k. dt on integration gives t plus c, where c is called a constant of integration. C is the constant of integration. C is the constant of integration. And when t equal to 0, when t equal to 0 means the reaction just begins. It is called the initial concentration. Concentration of A equal to A0. When the concentration of A becomes A0, at that time, at that moment, the time t equal to 0. And by putting the value of t here, that is When t equal to 0, A becomes A0, that is minus A0 equal to C, that is K into 0 is 0 plus C, or A0 equal to C. That is, our former expression is minus A equal to KT plus C, and here we get the value of constant of integration as A0, and substituting the value of C in this equation, it becomes minus A equal to KT minus A0. KT minus A0. And on rearranging this, when this A0 moves to left side, it becomes A0. Minus A0 becomes A0. Here already minus A equal to KT. Or K equal to A0 minus A divided by T. This is the integrated equation for a zero order reaction, where K is the rate constant, A0 is the initial concentration, that is when time equal to 0, A is the concentration after a time T seconds or T minute or T hours. Clear? This is the integrated equation. It is very easy to derive. You just consider a hypothetical reaction, not only A gives product, you can take any example like R gives product or X gives products, then corresponding differential equation you have to write, and you can arrange them into proper way, and finally you get the expression for the integrated equation for a zero order reaction. Okay, next is we have to derive the integrated equation for first order reaction. Integrated equation for a first order reaction. That is, for a first order reaction, same example, that is when A gives product follows first order kinetics or first order reaction. Then how we can write the expression or differential expression for a first order reaction? We have already expressed as a zero order reaction minus dA by dt proportional to A raised to 0 for zero order reaction. In the same way, we can write minus dA by dt proportional to A or A raised to 1. Because it is a first order reaction. Or minus dA by dt equal to K into A. On rearranging, that is like terms on same side, here there is dA, here it is A. On rearranging them, on rearranging this equation, minus dA by A equal to K into dt. Minus dA by A equal to K into dt. Next, we have to integrate this equation as in the previous case. And I repeat once more, consider a reaction A gives product which follows first order kinetics. You know, radioactive decay. Have you heard about this paleontology, that is study of fossils, carbonaceous material? Radioactive decay follows first order kinetics. And you know, carbon-14 isotope is used here. It has a half-life. Next we discuss the term half-life. 5,740 years is the half-life of carbon-14 isotope that is mainly used in paleontology. Paleontology means study of fossils. Carbonaceous material, we can calculate the age or time. Once more, that is, consider a reaction A gives product follows first order kinetics. then the differential minus dA by dt proportional to A or minus dA by dt equal to K into molar concentration of A. On rearranging this expression, minus dA by A equal to K into dt. Next, we integrate this equation. On integrating this equation, that is minus integral dA by A or integral 1 by A dA equal to K into integral dt, K into integral dt, that is minus dA by A equal to minus 1 by A dA equal to log A, that is natural log, ln natural log, ln A equal to KT plus C. In the Nernst equation, initially we express ln. ln means natural log. Natural log is converted to common log by multiplying with the 2.303. Then in this expression, next we find out the value of C, that is constant of integration. Constant of integration value, that is at initial concentration when T equal to 0, A equal to A0, which is called a initial concentration, that is minus ln A0 equal to K into 0 plus C, that is K into 0, 0. Minus ln A0 equal to C. Next, substitute the value of C in this equation. Minus ln A equal to KT minus ln A0. KT minus ln A0. Or when this minus ln A0 is taken on the left side, it becomes plus, that is ln A0 minus ln A equal to KT. Now this is in the form of log A minus log B. Log A minus log B is log A by B, that is ln A0 by A equal to KT. And this natural log, when it is converted to common log, multiplied with the 2.303, that is 2.303 log A0 by A equal to KT. This is natural log. Nowadays the logarithm is based on our class table is based on logarithm to the base 10. It is converted, natural log is converted to common log by multiplying with the 2.303. And from this, what is the expression for the rate constant? K equal to 2.303 by T log A0 by A, where A0 is the initial concentration and A is the concentration after a time T. The time is either minute, hour, year, anything. Depending upon the data given in the questions, the time is expressed either in second, minute, hour, year, etc. This is the integrated. This is important for the examination rather than the previous one, that is zero order reaction. Derive the integrated equation for a zero order or a first order reaction. The first order reaction is more, integrated equation of a first order reaction is more important than zero order reaction. This is the expression K equal to 2.303 by T log A0 by A is the integrated equation for a first order reaction. And for a zero order reaction, anybody remember that zero order reaction? Yes, K equal to A0 minus A, concentration of A0 minus A divided by T is the integrated equation for a zero order reaction. Clear? Next we introduce a new term that is called a half-life period. Half-life period. Half-life period means the time required to reduce half of its initial concentration. The time required to reduce half of its initial concentration is called a half-life period. Okay, the time required to reduce half of its initial concentration. As you know, the integrated equation for a zero order reaction is A0 minus A divided by T. The name half-life period. Half-life period means it is the time required to reduce half of its initial concentration. The time required to reduce half of its initial concentration is called a half-life period. All of you understand that? What is the time required to reduce half of its initial concentration? For a reaction, the time required to reduce half of its initial concentration is called a half-life period. That is, this is the expression for half-life period for zero order reaction. Half-life period of a zero order reaction. That is the expression for zero order reaction is A0 minus A divided by T is the integrated equation for a zero order reaction. When A equal to A0 by 2, A0 is the initial concentration and A0 by 2 is half of the initial concentration. T equal to T half. When T equal to T half is equal to A0 by 2. The time required to reduce half of the initial concentration is called a half-life period. When A equal to A0 by 2, T equal to T half, the time required to reduce half of its initial concentration is called a half-life period. Okay, half-life period is the time required to reduce half of its initial concentration. That is, by substituting the value of T and A, substituting the value of A as A0 by 2 and T as T half, this expression becomes K equal to A0 minus A0 by 2 divided by T half. A0 minus A0 by 2 by T half or T half equal to A0 minus A0 by 2. That is A0 by 2. Isn't it? 1 A0 minus half A0 equal to half A0 or A0 by 2. T half equal to A0 by 2 K. K equal to A0 minus A0 by 2. A0 minus A0 by 2. The numerator term becomes A0 by 2. And here T half. On just rearranging this, the expression for half-life is T half equal to A0 by 2K. From that, it is clear that the half-life period, the half-life period of a zero-order reaction is directly proportional to its initial concentration. Half-life is directly proportional to initial concentration. And the next thing is how to derive the expression for a first order. What is the expression for half-life for a first order reaction? That is, the integrated equation for a first order reaction is K equal to 2.303 by T log A0 by A, log A0 by A. When A equal to A0 by 2, when A equal to A0 by 2, T equal to T half. When T equal to T half, A equal to A0 by 2. Okay. Then K equal to 2.303 divided by T half log numerator A0 and denominator it is A0 by 2. Because A becomes A0 by 2 when T equal to T half. A0 divided by A0 by 2, that is A0 get cancels and 2 is on the numerator part. It becomes 2.303 divided by T half log 2. You know, the value of log 2 equal to 0.3010 or K equal to 2.303 by T half into 0.3010. That is, since log 2 equal to 0.3010. At least you have to study the value of some log. Log 2 equal to 0.3010. Log 10 equal to 1. Log 3 equal to 0.4. Log 3 equal to 0.4771. Log 4 equal to 0.6021. Like that. Otherwise, it is provided in the questions. And we can rearrange this T half equal to 2.303 into 0.3010 means 0.693 divided by K. 0.693 divided by K is the expression for half-life of a first order reaction. And what is your prediction? Whether the T half or half-life of a first order reaction depends upon its initial concentration? Is it? No. That is, half-life of a first order reaction is independent of initial concentration. Then you can conclude that, or in other words, question asked like this: derive the integrated equation for a reaction that they didn't mention whether it is first or zero order reaction. Derive the integrated equation for a reaction whose T half is independent of initial concentration. Whose T half is independent of initial concentration. And we can just consolidate it about the integrated equation as well as the half-life period of zero order and first order reaction. That is, for zero order, the case of zero order reaction, K equal to concentration of A0 minus A divided by T And for a first order reaction, K equal to 2.303 by T log A0 by A. This is the expression for first order reaction. These two represent the integrated equations. That is, these two are the integrated equation for zero order as well as first order reaction. And the same half-life period of a zero order reaction, T half equal to A0 by 2K, where A0 is the initial concentration. T half is directly proportional to initial concentration. And for a first order reaction, T half equal to 0.693 by K. That is, for first order reaction, T half is independent of initial concentration. T half is independent of initial concentration for first order reaction, and for zero order reaction, T half is directly proportional to initial concentration. And in your mathematics, you have studied in detail about, there is a separate chapter called integration. When you are familiar with integration, it is very easy to just write the expression for a general reaction. As I already told you that not only A gives product, you can take any reaction, symbolic reaction, and proportional to that, you express the rate equation. Once you write the reaction as A gives product, and the next step the rate is minus dR by dt, not like that. If you take A gives product, you write the expression as minus dA by dt. The negative sign indicates that the rate of reactant decreases with the concentration. And next, there is in the next part, studied about the numerical based questions based on the basis of this integrated equation as well as half-life period. You studied in detail because sometimes I think this is the last part of your chapter, that is chemical kinetics, and the other part is the temperature dependence on reaction, that is Arrhenius equation like that, and also the collision theory, collision frequency like that. That is this year the topic is deleted. And last part is about how to solve the numerical based questions on the basis of this integrated equation as well as the half-life. Okay, that we'll discuss in the next class. Okay, thank you.